So before I'll just post
Yes.
something on the chat box so that participants can have a look at the code that would help them. There is supposed to be some sort of a hands-on activity during the session. So you can refer to this link. It's a small Python script which you can run in Google Colab. No need to worry about anything within it. And if it is not running, don't worry. We will go through it together.
Okay,
so
sir.
I think, yeah.
Okay.
Yes.
So all the participants, now the resource person is here. So we'll start the second session of today. So now may I request Dr. Mona Lisa Mohanty, please kindly introduce our resource person for this session. Thank you, Mona.
Thank you, ma'am. Hope I'm audible this time, ma'am.
Yes, you are audible.
Jai Jagannath. Once again, good afternoon, everyone. Now, ladies and gentlemen, it's the time for our next session to begin. Allow me to introduce to you the speaker of this session, Dr. Pratik Shah. Dr. Shah has completed his BE in Electronics and Communication Engineering from Gujarat University in the year 2003. His MTech in ICT from Dhirubhai Ambani Institute of Information and Communication Technology in year 2005 and obtained his PhD in ICT from the same Dhirubhai Ambani Institute of Information and Communication Technology in year 2012. Dr. Shah has worked as JRF and SRF with Naval Science and Technological Laboratory Vizag on a project titled Estimation Filters for Target Tracking Problems. He has also worked as a faculty with the Department of Electronics and Communication at the LNM Institute of Information Technology for 2 years. He has joined IIIT Barodara as assistant professor in year 2013. He has recently completed a project with Indian Meteorological Department on data-driven weather forecast problem in year 2020-21. He has organized multiple faculty development programs sponsored by AICTE ATAL on artificial intelligence and data analytics. He has conducted 2 training programs for Tata Power on predictive maintenance during year 2019-2020. Currently, he is the project coordinator for Guj Coast sponsored supercomputer facility at IIIT Barodara. Dr. Shah is a certified NVIDIA University Ambassador and instructor for NVIDIA Deep Learning Institute workshops. His research interests include artificial intelligence, differential geometry, and signal processing. Today, Sir will be delivering a talk on neural network as a universal function approximator. I hope all the participants will get benefited at the end of this talk. Now, may I please request you, sir, to deliver your talk? Sir, over to you.
Thank you. Thank you for nice introduction. So longer one, but thank you.
Welcome, sir. Over to you, sir.
So I'm slightly old school and I'll not prefer slides. So I'll be writing through the session and I would encourage participants to stop me as and when they feel there is a question or there is something which I have not clearly mentioned in the details. Don't feel that this is going to be a very heavy math-oriented, application-oriented talk. This is going to be a very basic fundamental talk, and I would not call it a talk. It's a discussion, deliberation on a different view on deep learning pipeline. So we'll explore compositionality of the deep learning pipeline. And I'm sure that many of these things are known to you. And some of these things will be new for many of us. Along with that, let me just begin with slight history in the context of AI itself. So I'm sure you have seen these diagrams before, so I'll just show something here. So this is what I call everything that comes under AI. So you know Venn diagrams, correct? And this is a part of it, which I call machine learning. Maybe I can use a different color if you want. And within machine learning, there is a small circle, which I call deep learning, correct? So this is DL. So you see that the type of arguments that we are going to see in this discussion would be limited to this green region. That means we are going to look at problems which are being solved by deep networks, and the typical problems that we encounter in deep learning are one or the other way. You can classify them broadly into either a classification problem or a regression problem or reinforcement learning problem. Those who don't like reinforcement learning, you can think of these as a control theory problem. So it originated from control theory. A lot of control theorists have played major role in development of reinforcement learning. So it's a highly mathematical discipline, and it involves Markov decision process and in some way decision-making system itself. So these are the major three categories of problems that you encounter in deep learning paradigm. Now, you may argue there are other things, but they fall outside deep learning. You can think of many different tasks: reasoning, probabilistic reasoning. Yeah. Was there a question? Okay, let's continue. So today we are going to look at this green box here, and so that means we can start with some sort of a history here. It all started in 1943 with a paper by McMulloch and Pitts. What was the paper titled? Paper was titled Logical Calculus of Ideas Immanent in Nervous Activity. So this was the paper which came out, and then this is the first instance recorded where we see that there was a discussion on neural network. So Warren McMulloch was a neurophysiologist and Walter Pitts was a mathematician. They came together, wrote a paper, and they modeled the very first. It was the first attempt to model neural network using electrical circuit. I'm sure that you will be able to dig out details. I'll not go by the references and so on, but you are required to look at references. And the paper was difficult to read, and because of its spatial notations, because you understand the mathematics and neurophysiologists coming together writing something, it's a very tricky thing. So that was a difficult paper to read in context of the research paper. Then in 1949, I'm just giving you a brief history that why and how we have reached the current state of affairs in deep learning. There was a nice paper which was named Organization of Behavior, not organizational behavior, but organization of behavior. And this was by Donald Hebb. Those who are aware of some sort of machine learning background, they know what is Hebbian rule of learning for associative memories and Hopfield networks, correct? So I'll just, maybe I can make a point here. Hebbian rule of learning. This is based on simple correlation. Correct. And there the discussion was on Hebbian cell assembly and Hebbian synapse. It's considered as a general framework for relating behavior to synaptic organization. So how the network gets the weights and how the synaptic junctions are reinforced and how the synaptic junctions are formulated in our brain. This was the paper which talked about synaptic organization, and again this was also a good attempt. Then in 1957, remember these are still all philosophy theory sort of ideas, correct? Not tasted yet in terms of computation. 1957, Frank Rosenblatt and he published a paper which is considered as the I think most of us agree that this is the first paper on perceptron. This was the first paper on perceptron. Perceptron is a neuron, correct? And he is known for electronic device that he constructed in accordance with the biological principles. And these perceptrons were initially simulated on a small computer, a very small computer. I'll just show you the size of the computer, and that would give you some idea that what was this perceptron. So they used this machine. This was the machine. This is IBM 704, and this was used for modeling one perceptron. Interesting, correct? So this is 1958, a probabilistic model for information storage and organization in brain. So it came up in Psychological Review, 1958. So this was the computer, and since we all are in some or the other way connected through electronics, so you may like to look at what was inside it. So this was the vacuum tube circuit module inside IBM 704. Remember, semiconductors were not there, and so things were slightly more bulky. And this is an example of a small circuit module inside the IBM 704. And then because of this development, the press, and specifically the Western press, they like to fantasize a lot, fiction and things like this. We also do the same. So New York Times, it was a huge success. And this started what I call as AI hype. So they started saying that everything can be solved with neurons and neural networks and so on. So this was a time when I usually describe this as AI hype. Why hype? So if you look at today, the way in which we describe perceptron, what is a perceptron? Perceptron essentially is a linear classifier. We'll see what it is, but this is in some sense just a linear classifier. And then people started talking about, yeah, this can solve almost every problem. And then all went well with several initiatives, starting from romanticizing AI and creating machines which were intelligent. And you know the story behind Rhett going through a maze, searching for a path for food and so on. So all the efforts in terms of creating miniature mechanical, electrical devices to mimic human intelligence in some or the other sense. Then came a very remarkable book called Perceptron. This was by Minsky and Puppet. A very nice book, even for somebody who wants to start looking at things which can be done by neural network or no. You will find a definitive answer in this book. It's a nice book. It has 3 parts: algebra, then geometry, and then things which you can solve, which you cannot solve. So it's a very crisp, nicely written book, slightly old book, but still relevant. So you will come to know what you can solve with deep networks and what you cannot solve with deep networks. That answer lies inside this book. This is the starting point of the discussion that I'm going to enter into. So there was a lot of criticism, and this book said that you cannot solve everything using perceptrons, and so all was silent till 82, 85. And then people started talking about cooperative and competitive neural networks. They started putting together large networks, because by that time the computation power was becoming cheaper and cheaper and available, unlike today. But yeah, they had some computational power, so they could do certain basic things. And neural computing actually started with a conference. So 1985, the first conference on neural network was initiated. There were around 1800 attendees. So this is all we know so far, correct? So why did I give you this 1982-85 picture here? After that, what happened? After that, if I look at the field today, what is learning? In the context of deep learning, what is learning? And the major question that we would be answering is slightly more interesting. What is the role of data in learning? So when you have large amount of data, the typical scenario is that you have training set T, which is containing the pairs xi, yi, where xi is the input. This belongs to some n-dimensional space, and maybe I can use small n because I'm going to use a lot of letters here, and yi, which is a corresponding output, which belongs to Rm. Correct. And in case of classification, this yi could be just a class label. So this would be a class label assignment. For regression problem, this could be any output vector of dimension m. So essentially, we are trying to find out a mapping from input of dimension n to output of dimension m. Okay, great. So let's talk about classification problem. In classification problem, we typically say that this yi's are going to be the class labels. And the question that we pose is in terms of, tell me the probability of having output yi given that the input is xi. So find me a probability model given this data. Find me a probability model that tells me the probability of yi given xi. Now, if you look at this equation more carefully, this is not just dependent on xi, but since I said you are learning a model, that means you are not just taking in xi, but you have a model with you which has certain parameters. These parameters I'm going to call theta. This theta is given. Now, interestingly, what I'm going to do is I'm going to say that this is not just theta, but you also have dependency while doing this sort of inference. You have a dependency on something else also. And that something else is what? The training data set. So maybe I can remove I from here if you permit me, since I'm going to say that training is different than the inference. So you don't have to confuse yourself here. So I'm saying that y given x, and I'm given the training data and theta. So it is not just theta, arbitrary theta, but theta learned from training set T. So you see training playing a role in creation of a model. And then further to this, you have another interesting view, and that you will agree, those who have trained even a small neural network, they realize that the way in which you pass on your training samples to the network, that means the order in which you provide the training samples to your network, may give you different parameter settings. The weights inside the network may differ if the ordering of training samples which are given to the network is changed. That means some sort of dependency on the order in which the data is provided or training is conducted, and this R is called a seed or a random number, which will decide which order you are going to select for training your neural network. So this is the problem by and large of learning. So you want to learn a model theta, parameter theta, with training set T, such that you can answer a query where the query is what is the probability that output is Y given the input is X. Simple problem statement, correct? Okay. But there is more to this picture. And what is that more? So I'm going to call it a hidden story, because not many, I'm sure that not many of us are aware of this story. So this was 8th August. Any guesses on the year? Difficult. 1900 in Paris, Sorbonne, Paris. Beautiful place. And what was done there? Any guesses? No. There was International Congress of Mathematics. Meeting was going on. And something interesting happened there. And what was something interesting that happened there? There is someone known as David Hilbert. David Hilbert, at the Congress, this man was there. I'm sure you have heard about Hilbert transform, Hilbert spaces, and blah blah blah. Correct. David Hilbert, he presented 10 unsolved problems in mathematics. At that time, which in his opinion should be the main goals of mathematicians in the 20th century. Remember, this was 1900. So he was saying that these are the 10 problems mathematicians should focus on for next 100 years. Now you can imagine the importance of each one of these problems, correct? The actual complete list was 23, but 10 were presented in the Congress. Out of this 23, we are interested in 13th problem. And what was the 13th problem? So the 13th problem goes like this. There is an expression, a polynomial in X. If I remember it correctly, this is what it is. Bx square plus cx plus 1 equals to 0. Yeah, this is it. And the question that Hilbert asked goes like this. Is it possible to write its solution, which is X, as a function of what are the parameters inside this polynomial? A, B, and C. As a function of A, B, C, but not just a function. What is more important is the second part. As a composition of, sorry for that, a finite number of two variable functions. I hope you see the problem now. So we all are in communication electronics, correct? So when we take a function, we talk about some sort of decomposition of function, correct? So we always argue about decomposing function in terms of suitable basis. This is a typical vector space approach to our signal systems and communication and so on, correct? Or your Fourier, wavelet, and many such transformations which are based on this idea that you want to decompose a given function or a vector in terms of suitable basis. There is a difference between decomposition and so this is like a superposition of many basis vectors. So this idea is superposition idea. So you want to write down a function f of x as a summation of many phi i's versus composition. So let's see if I can convince you of the idea of compositionality. So here I'm saying that you don't give me this dumb superposition, but give me something interesting. And what is something interesting? You see the difference between them? One is superposition, the other is composition. So Hilbert's question was, don't just give me a function of x, function of ABC. Give me a function of ABC. So let's see, what is it that I'm looking at? I'm looking at x as a function of ABC, but not just any f. This f has to be defined in terms of finite number of two variable functions. So that means he's saying that I have phi1, which is a two variable function, then phi2, which is a two variable function. I have finitely many of them, and I want to write down this f in terms of composition of some sort of composition of functions. So I want to write down f in terms of composition of functions. Any questions up to this point? Is this point clear? This is most crucial point of our discussion. So if you are not satisfied, you can push me. Okay, maybe I can give you an example. That would be a good idea. So let's see. What do I call a function of this type? Okay, let's see. So f ABC, just an example. I'm not giving you the solution, but some f prime ABC, which I'm defining as max of maybe sine of A plus B and C. Okay, so what do you see here? There is a function inside this. There is another function which is a function which is saying that just C. So this is a function which gives you C. This is a function which gives you sine A plus B. It's a function of two variables. And max is obviously a function of two variables. It's a max of two. And this function, if I call it some pseudo function psi, then psi is a function of A and B. And this is psi2, which is a function of A and B. And so maybe just C here. So you see, this is what I mean by composition of functions. Just an example. Clear? Any questions? Okay, so the interesting part is a generalization of this problem that Hilbert posed. Hilbert said that you just give me a solution of this form. Is it possible to have a solution in this form or not? But then a generalization of this form of this problem in the class of continuous functions was asked by your friend Arnold, who was student of Kolmogorov. And this was in 1957 that he was able to answer a very interesting question. What was the question? Can every continuous function of 3 variables? So he said, don't worry about just solving that problem particularly. Look at any continuous function of 3 variables. And I'm asking this question, can it be expressed as a composition of finitely many continuous functions of 2 variables? This is interesting. So he did not solve a particular problem, but he actually answered a very general question. So I can just reproduce his theorem here, but obviously it's not going to be very helpful. Just an aside, so you can, in free time, you can have a look at this result. It's a very powerful result. Yeah. So he said that you can actually express continuous function of 3 variables as a composition of finitely many continuous functions of 2 variables. This was a remarkable thing. And but the problem is, knowing that this can be done does not mean that you have a way of constructing a solution. Correct? Great. But then Saibinko in 1989 result came up which was more related to neural network. Now we are moving into our major topic of discussion for today. So let me just try and see if we can connect things here for you. So for me, a neural network is collection of neurons put together. Correct. And what is a neuron? So here is a neuron. Neuron can be thought of as partitioned into 2 parts. One is a linear combiner, another is the non-linearity part, which is activation function. So this is what I mean by linear combiner. And this is your activation function, which is typically the way in which you introduce non-linearity in your output. And what is input and what is output to the system? So I said, correct, you remember I said very clearly there is a training set which is having input xi and output is yi. And what is this xi yi doing here? Xi belongs to Rn, reiterating it for sake of completion, and yi belongs to Rm, and what more? I corresponds to the training sample. Okay, now each of this xi is an n-dimensional vector, correct? So I can think of this as x1 to n, which is the input to my neuron, and this is the output y. And what is y here? Y is nothing but, it is defined as sigma, which is activation function, composition, summation of I running from 1 to n. On each of this edge that you see here, there is going to be a weight associated. which will be put on the edges. So what happens is x1 gets multiplied by w1, x2 gets multiplied by w2, and xn gets multiplied by wn. And so you have a nice inner product between input vector and the weights here. So you get xi, wi plus a bias, which is typically a number b. So this is what your output y would be when you supply x, which is a vector, as input, given the activation function. This is the definition of a single neuron. The question is, I have not still defined what is sigma. So sigma, you can think of sigma in multiple ways. The easiest way would be to give you some examples and show that what are sigmas. So I'm going to give you 3 examples. Maybe I can give you more, but these are sufficient for time being. So the very first one is this yellow graph. I'm going to call this as input, and this is output. So this is input, this is output. You remember that functions can be written in terms of input-output relationship in the form of a graph. So that's why we call them functions. So this is the first graph. This is called ReLU, rectified linear unit. So what it does, any input which is negative will be suppressed by the ReLU unit. The positive values will be allowed to pass through ReLU without any change. So the slope of this line is 1, correct? Okay, what other function are you aware of? There is 10h. 10h is also a good function, and what will it do? It will map values in the range of -1 to +1. Okay, what about the other any other function that you are comfortable with? Maybe yeah, you can just do loud thinking and let me know what other functions do you remember. Sigmoid, I guess yes, you remember sigmoid. And how does it go? Sigmoid is essentially a function which at 0 will be half, and then it will try to approach 1 in the positive side, 0 on the negative side. So this is how it goes. Depends on the slope, so you can actually do something better. I think this should be fine. Okay, so these are 3 basic. There are many more. There are probabilistic, stochastic activation functions also, and there are interesting things which you can do with activation functions. For our discussion, it doesn't matter which activation function you pick. As long as you pick a nonlinear function, your results are going to be true. So that's very important. Yeah.
Sir, can you explain that bias part little bit?
Bias. So
bias,
if you
that B.
Yeah, so B is some sort of a parameter which is supplied to this neuron so that your inside function, the inside argument, is not just an inner product between xi and wi. There is a control to ensure that you have some sort of an affine transformation of input. So this is a scalar number, correct? And you are adding a bias term to it. So we'll talk about it. Maybe we'll get some time at the end also to talk about it. So when I talk about a model will contain. So maybe I can highlight it here itself. So model essentially is W and B. So if I'm looking at this neuron, the way in which I can characterize this neuron is with the help of its weights, input weights, and the bias. So if I know these values of Wi and B, I know how to pass an input X and produce Y. Given that I know what is sigma, given that I know what is Wi, I know what is B, I can supply X and produce Y. Correct? And reason there is a B here, you can just relate this with your linear classifier. Correct? So you would like to have a line which will classify points from 2 different classes if it is possible to do so linearly, in the sense that they are separable in terms of straight line or a hyperplane. So if your data set is possible to separate in 2 classes with the help of a separating hyperplane, we call such problems linearly separable data sets. So in this linearly separable data sets, you would like to find out an expression of a hyperplane, or for that matter, in two-dimensional space, we would like to find out expression of a straight line, which divides your space into two equal parts, so that one part contains one type of data and the second part contains second type of data. So that's why there is a expression which is similar to a line. So this is like a affine or a hyperplane. Does that answer your query?
Sir, then how here to we will from the training set we will calculate the value of Wi and B.
Yeah.
But I cannot understand why we should include that B. We can calculate only Wi.
Yeah. So let's see. You have this yellow and reds are xi y. So these are xi y's. Yi is a label which is yellow and red. Let's say, or +1 -1. You remember SVM, support vector machine? You had +1 -1 on the labeling. So you are trying to find out this straight line which is in green, so that points which are on the right would provide you label +1. So when I plug in this red point means when I actually take the coordinates of this x point, x1, x2, and then feed this into the expression here, I should get a +1. Same way, if I do this for yellow, I should get -1. Now that means I'm searching for a straight line equation which is in green. And how would you write the expression of a straight line?
Y equal to mx plus c.
Correct. So that's where this B comes from. Now is it okay? This is another way to look at it. Great. Okay, now once we are through with this, next target is to do something more interesting with your single neuron. And what is that idea? So sorry for that. I'll actually take help of things which I have already pre-written for you, so that we don't waste time. Excuse me for that. I guess you will not mind if I do that. It takes a lot of time for me to actually draw something like this here. Sorry for this, but yeah, it was necessary. Is it visible?
Yes, sir.
Yeah, so this is your input. So I'm going to write arrows here. This is your X input, and this is your output Y. So Y is an output which is a vector of dimension m. X is an input which is of dimension n. And inside this black box, what you see is a configuration of neurons where I have put up neurons in a layered fashion. So this particular part is your first layer. This is your first layer, N1, and there are N1 neurons in layer 1. Same way, this is ith layer. You have Ni layer, Ni neurons, and the output layer, you have M neurons. Correct. So you have input which is N, output which is M, and inside this there are many layers, and each layer contains N1, N2, N3, and so on number of neurons. Correct. So whatever we did for one neuron, now this is one neuron that we saw earlier. You can do the same for neuron 2 here. So all of this would feed their input to second neuron. And the output of second neuron will be marked here. Okay, so you have input, which is of dimension n. And then you have first layer, which has N1 neurons. And so if I demarcate the weights, you will realize that what I have done is for input x1, the weight connecting x1 and the first neuron is W11. Weight connecting x2 and neuron is W12, W1n, and so on. So what happens is after this first, so I'm here right now. After this first layer, the output will contain n1 number of real numbers. Correct. And how does this number n1 number of outcome arrive? So they are actually nothing but multiplication of your input vector x with a matrix, a weight matrix, which is describing your first layer here. So these are W11 to WNN. So these are the weights of your first layer multiplied by vector x plus bias which is there for each of the neuron in the layer 1. So B1 to Bn1. So now you see there is an activation function sigma operating on a matrix multiplied by a vector plus a bias vector. So this is an affine transformation from Rn to Rn1. So what we did, you can think of this as X, which is in Rn. You passed it through first N1 neuron layer. You get maybe intermediate output, which is going to be in Rn1. And what is this Rn1 going to talk about? Sigma of Wx plus B, and this belongs to Rn1. And this continues. And at the end, what do you get? At the end, what do you get? Y, which is belonging to Rm. But when you look at Y, which is belonging to Rm, what is expected there? This is going to be, so if the activation function is sigma 1 here, and if there are k such layers or capital N such layers, then I'm saying that each of this neuron layer output will be provided as input to the next layer, and the next layer will produce again output which will be fed to the next layer and so on. And finally, I arrive at Y, which is Rm. So what exactly I am doing here? I'm doing some sort of function composition. So if I think of this transformation here as an affine transformation T, it's an affine transformation T, correct? So that means I'm first applying T1 on X. So I'm here right now. I'm applying T1 on input. Then I'm passing it through activation layer. So I would not say layer, activation function. So sigma composition T1. So this is what we mean by composition, correct? Sigma applied to every argument of T1x. Then this sigma T1x is supplied to the second function T2, which is your second layer weight matrix plus biases. Then it passes through again sigma, then again composition T3, it goes up to Tn. So you are essentially saying that this is a function fx. You have a function f of x, which is nothing but a composition of many such affine and nonlinear functions. Are we good? If you want, I can replace this sign here to convince you that we are now talking about something which we started with. It's difficult to keep track of all the brackets, but yeah, this is what we are doing. So X as an input passes through a lot of functions and you get your output, which is Y. So what is it that we are doing? We are doing some sort of composition of lot of functions. Yeah, any questions up to this point? This is the easiest thing, and I think people get confused because they don't give sufficient time to understand what exactly a neural network is doing. Are we good? Can we proceed further? Okay. So now what is the next step? So this is something which is a feed forward sort of a thing. You might have heard about it, correct? So if I give you all the weights of your network, so when I say all the weights of my network, so here is the idea. So remember our discussion earlier? The learning problem had theta here. What was the idea? Theta is the model parameters. And so if I think of deep network as a model, the parameters of this model are theta, and theta are described in terms of W and B. I corresponds to the layer. So layer 1, layer 2, layer 3, layer 4, layer K, and I also corresponds. So BI, B1, B2, BK are also the biases for each layer. So theta essentially is a very huge set of parameters containing all the weights of intermediate layers and biases. So we are through with theta now. So we know that now y is a function of x, but the function of x has parameters which are theta. Now, something more interesting. I took sigma as a same function throughout, correct? But you can argue that I could take 10h here, then I can take relu here, then I get sigmoid here, I can take softmax here. So I can change these sigmas, correct? You can do that. You can actually have sigma 1, sigma 2, sigma 3, and so on. Nobody stops you, correct? This notation or this sort of network that you created is called a sigma net. I'm going to refer to this as sigma net or a neural network. Why sigma net? In literature, typically we say that sigma is a collection of nonlinear activation functions. So this will be sigma 1 to sigma k. You can pick any one of this sigma and you create a network. We are going to call it as a sigma net. So sigma 1 could be relu, sigma 2 could be sigmoid, and so on. So f theta is nothing but a sigma net. Any conclusions, any doubts, any questions? And the problem is, how do I find out this theta? So how do I find out this theta? The problem is very simple. I am given the training sample. I am given the training instances, which are xi, yi's. And one of the way in which I can do this, because this is like a regression problem, yi is given to me, output m dimensional vector is given to me. So what I can do is I can actually try to find out the arg mean for theta, and so theta is essentially wi's and b. Find out the weights of your network and biases such that when I supply a particular training instance as input to my network, correct, along with parameter theta, and I compare it with the actual output yi, they should be very close to each other. And one of the way in which you can measure this similarity is in terms of, remember what is it? What is this? This is a vector. Yi is a vector. Xi is a vector. Fxi would be a vector of dimension m. And so I'm going to talk about distances between them as an error vector. And so I'm saying that norm of this quantity is to be minimum. But then do you mean that norm of only this input output pair should be minimum? No, you want every one of this sample to have this property. So you want your network to model every data point which is there in your training set. So you would like to have some sort of aggregate behavior that for every every sample in my training data set, I should be able to find out theta such that this error summation is minimum. Correct. And this theta is then your optimal theta, which minimizes this cost function. This cost function is typically called mean square error. I think you know about it. I don't have to talk about this in detail, but yeah. And one of the way in which you can do this is you can apply your gradient descent rule. Simplest thing is to think of these as a function of variables wi and beta I. Take so if this is the cost function, this is the cost. Correct. This cost function depends on theta. Correct. Once I give you xi, yi pairs, this becomes a function of theta. And so once you have the function of theta, what do? You would take partial derivative of this function with respect to unknowns, which are the parameters, equate them to 0. This becomes your gradient. And then you start with arbitrary initial point for w and b, and then move in the direction of opposite direction of the gradient so that you can reach the minima in the hope of reaching minima. So that's the idea behind the learning part. So learning is nothing more than gradient descent, because this f is a composition of many functions. You do this in layer by layer fashion, and so there is a name given to it which is called as back propagation. I'm just giving you some idea. So backpropagation is very clear the moment you say that this is f, and this f is a composition of many functions. So you have to do it layer by layer, and that's why we call it backpropagation. You update your weights from right side to left side, and that's why we call it backpropagation. So gradient information is passed from right to left, from the rightmost layer to the input layer. That's how the learning takes place. There are many challenges and many problems associated with backpropagation. We don't have time for that, but yeah, essentially, this is what is the learning in the deep network. Okay, any questions up to this point? Yeah, feel free because this is important. Okay, great. So let's see. I have still one problem. I have not talked about what is T here, correct, and what is R here. Let me highlight that part. This cost function is actually a tricky thing. There are two things. Very first thing is the cost function depends on data. Do you see this point? Your training set is xi yi. So when you divide your entire set into training and testing or validation set, then the way you decide to take training samples will define your measure of goodness or measure of fit or mean square error or the cost with respect to which your network is going to learn your parameters W and B's. If I change my training set for the same problem, when I say same problem, let's see what I mean by same problem. So here is the nice explanation. So I find this appealing. So I'm going to take this anyway. Here is the picture, I think. Okay, so you see a graph here. You have the horizontal axis is x, which is Rn. Vertical axis is Rm. Input is x, output is y, and the black is the function that you are trying to find out. So for given x, what is the y is described by black function, which is unknown. So this is unknown. But what do we know? We don't know the function f star, but we know at certain locations marked in green, x1, x2, x3, x4, xk, what are the values of y? Correct. So only for this small part of training instances, I know the xi yi pairs. So if I sample my black function differently, I get a different training set. Now you see that the cost that you are deriving is actually a function of training instances. That means if I sample my black function differently, I get a different cost. Okay, that's good. That's a very good thing. Let's say you decided that you have identified a parameter W and B for a sigma net, and because of that parameter setting, you get this yellow function as a mapping from x to y. And your friend decided to do a different set of setting. He gets a different function f prime, which is in orange. Okay. Now my question to you is, how do you say which function is a better approximation to black function? Just look at it visually and tell me which function is a better fit, orange or yellow. Is the graph visible? First question. So because I'm not able to see it myself, so if you can just help me.
Visible, sir.
Great. So which graph do you think is more closer? Yellow or orange? A difficult question, correct? Now let me ask you this question. What do you think, which graph is closer for green points? So if I just consider green points, with respect to green points, which graph is closer to black? Which graph agrees with black?
Orange one, sir.
Orange one. Why? Because if you look at it carefully, this is closer, this is closer, this is closer. Actually, it has been created like that. I wanted to convey this point. Here there is a difference, but this again is closer. So with respect to this x1, x2, xk green, the orange one is closer to black than yellow. What about red one? Obviously, I have told you the answer. For red one, it is the yellow which is closer. So you see now the training data set decides how good your approximation is. And so a function which is not a good approximation for you may become a good approximation if the training set changes. So the objective here is, by doing this gradient descent on training set, I'm going to create iterates of sigma nets. So I'm going to create F1, F2, F3, and Fn, maybe Fk, such that eventually this will approach F star. I'm creating F1, F2, F3, so that finally, if I do proper gradient descent, I'll at least be able to ensure that on the known training samples, my function definition of Fk agrees with definition of F star. I don't care about things which are not in training set, but at least within training set, I should be able to ensure that Fk and F star are agreeing on training set. Is this clear? This is fantastic. So now we have covered a lot of grounds. So as I said, gradient descent, I think you can just straight away describe these as W as a set of all parameters, Wt plus 1. You start with initial W, weight, and then step size, gradient with respect to W and B, and the error function for W and B. And the error function is what? This is the error function. Okay. This is sometimes called as learning rate, and there are many ways in which you perform optimization. This is the easiest one, and you can immediately start doing it. Great. So when we say this this nice behavior F1, F2, F star, we are actually saying that F star is original function, the black one which you try to optimize, which you want to approximate, and the neural network functions are all Fk's. Correct. And as k grows to infinity, I want this also to approach 0. This is the way in which you describe it. This is the norm between. So this is the norm on the set of all functions. Correct. So functional space is there, and you define distances or the norm between norm of a function, and norm of a difference tells you the error energy, or maybe the amount of error, amount of dissimilarity between F star and F. Correct. So this is some sort of a convergence behavior that we want to expect from our gradient descent approach, backpropagation approach. So when you are training, you are actually creating a sequence of iterates F1, F2, Fk, such that eventually Fk will be closer to F star. Nice way of looking at it, correct? And not a new thing to consider. Now comes the unofficial or informal statement from my end. So sorry for that, but yeah, this is something which I prefer to give as a metaphor. A network model or a sigma net I'm just saying that sigma net can be seen as a function approximator or a model generator. This is my version of it. And so what happens is, here is set of all continuous functions from Rn to Rm. So this is the way in which we write it. So these are a lot of functions. Each of this point in this region is a function of type Rn to Rm. So let's say this is my f star. This black dot is my f star, which is unknown to me. I'm given just a training sample. And what do? I start with a initial sigma net f. I call it f0, let's say. And then I create sequence of iterates. So from f0, I go to f1, then I go to f2, and then I go to f3, and then I go to fk, and so on. Such that, let's say this is the distance, epsilon. This means all those points which are inside this region are within epsilon distance from f star. So essentially it means norm of f star minus f is less than epsilon within this region. Any f inside would have this behavior. Now there are very strong results which says that if you do your training properly and your model is particular type, then you can create iterates of your f naught, your sigma net, so that eventually you will land up inside this region. This informally is a definition of what is known as dense set. So what it says is, let me tell you an example of denseness, and then I'll just conclude this theory part. We don't have much time. We have to talk about implementation of this also, because this is important. Theory is good, but what can I do with it in practice is more relevant for engineers. So let me just quickly go through denseness. So we usually say that set of rational numbers, which is subset of set of real numbers, is dense in R. So Q is dense in R. So what do I mean by that? I mean by this, on a real line, there are rational numbers, correct? So you pick any rational number. Let's say this is rational number Q. Right. Q is dense in R. So what do I mean by denseness? If I pick a rational number, sorry for it, let's say start with a real number, let's say root 2. Root 2 is irrational. I'm sure that you know about it. So you start with any irrational number R. You take a small radius around root 2. No matter how small you want to take. This epsilon is nice character. You can take it as 10 raised to minus 15, 10 raised to minus 100, no matter how small you take it. When I say Q is dense in R, so what it says is, given the irrational number root 2, you will always be able to find out a rational point in the interval, in the epsilon interval around root 2. So that means no matter how you define your irrational number, there will be a rational number which will be within epsilon distance available on real line, which is very close to square root 2. So actually, instead of working with root 2, I can actually work with Q. Same way, here also, I hope you see the point here. So what I'm trying to say here is, in this functional space, no matter which function you take here, f star, you will always find a sigma net function. For every epsilon, you will find out a sigma net which is within epsilon radius of f star. And then you can use this f star as an approximation. So you can use this sigma net as an approximation to f star, which is a very strong result, which says that for every function practically, which is Crn to Rm, you will get a sigma net, which will approximate f star within whatever resolution you want. Epsilon is like a resolution. You can make epsilon as small as you want. So what it is saying that even if epsilon is 10 raised to minus 50, you will be able to find out a sigma net which is within that distance from f star. This is fantastic, correct? If you don't trust me, I understand. So don't worry. So there are nice results of this type which are available in tabular form. This is from a paper which is a recent paper, 2020, got approved in 2021. So it says that there are a lot of theorems which say that with activation function like ReLU, I can actually approximate all the functions of type L1, so Lebesgue measurable functions from Rdx to R. So dx dimensional space to real number. I can actually find out such a neural net, sigma net, which has activation ReLU, and the width of the layer. Remember this W min is the width of the layer is dx plus 1 to dx plus 4. So within this width, so I said that each layer had n1, n2 neurons, correct? The size of this layer is defined by width. So what it says is you require at least this much of width to approximate a function here. So this guarantees that you will always be able to find out a sigma net of appropriate type to approximate your function. Those who are interested can refer to this paper. I think I am okay. I can stop here as far as theory is concerned. If you have any questions, I'll be very happy to answer. Now, before I take questions, remember I said that this theta is parameter and it depends on minimization of this, but this minimization or the cost function itself depends on the data set xi yi. So that closes our second point. So I have dependency on t now, and because we cannot process all the data together simultaneously to do the gradient descent, we do some sort of stochastic or batch processing. So that means in a particular sequence, you provide the training instances to your input for training. And that means you are picking a set of samples randomly from the training set for deciding on the batch. So you do batch gradient and so on. So R is a seed, a random number generator seed, which decides which batch or which samples you will pick for processing or for updating your weights in a particular order during run of a one epoch to go through all the samples in your training set. So that says that what is this py x r t theta? I guess that verifies all the three interesting parameters r, t, and theta, which are in the model, which are hidden from users, but now you see they are there. It's not just theta, it is theta, t, and seed. Okay, any questions up to this point? Any doubts? Time that we move on to our interesting part, which is our hands-on session. Yeah, any questions, any doubts? Please feel free.
Sir, how to determine the number of layers?
Yeah. So let's keep this question for last. Let's move on to the hands-on session. Time seems to be running faster than thought. So maybe I can share my tab. I would request you to open the GitHub code, which I have circulated to you via a link in the chat box. Just let me know if it is not accessible. Is it accessible?
Yes, sir. It's opening.
Yes,
Okay.
sir.
You also would have to tell me that my screen is visible and the font size is legible.
Yes, sir. Your screen is visible and font size is fine.
Great. So let's move forward. So this is a small notebook created to provide you with some idea about approximating functions and functions which are very notorious in nature. So it is not a very simple sort of function which we try to approximate. Very complicated functions can be approximated, and that's what I wanted to just show you here. So I'm not going to do any numerical analysis here, but there are two purposes behind giving you this notebook. One is how you create your model from scratch using Keras and TensorFlow. Second is how do you train, how do you compile a model, how do you store a model, and that was another hidden incentive which was there when I designed this notebook. So just bear with me for a while. Those who are new to Python, no need to worry about it. The first part is just calling all the libraries which are going to be used in our program. Those who are comfortable with MATLAB or Octave or Scilab or any other computing language, you are free to explore this in your own language. Python seems to be easiest, and a lot of tools are available. TensorFlow and Keras is very powerful in terms of not asking you to code too much. I think MATLAB also has a lot of good libraries now. You can use MATLAB also if you have access to MATLAB Cloud or MATLAB for your institute. Okay. We work with open source tools because we have this policy of promoting open source development. So I recommend you to work on open source platforms and frameworks. Okay, so let's start with the first one, which is a sinusoid function. So you see that x is a randomly selected value between 0 to 2 pi. Correct. 1000 samples from 0 to 2 pi. So it could be anywhere. So xi's are all randomly picked. It is not in order, any xi. And then y is just 1 plus sine of x. So it is just shifted by unit 1. So everything is positive. Just to give you an idea. So this is what you see in the graph. Okay, so now what I'm going to do is I'm going to see that this x train is my training data, y train is my label or the output. So this is input and this is output. And because this goes inside the network, I need to create them as a matrix which is going to be part of your input. Okay. So it's a list essentially. Okay. Then I start building up my model. And the model I decide to pick is, remember N1, N2, N3, N4. So I'm saying that the first layer is having 16 neurons with activation ReLU. So 16 neurons in the first layer, densely connected. That means every input is connected to every node. Correct. That's what we mean by dense layer. So there are 16 neurons. Input is 1 because x is just a scalar number. So there would be 16 weights in the input layer plus 1 bias. It passes through a ReLU activation function, which is again known to you. And then I'm assigning initial uniformly distributed weights to begin with my F0. Your sigma net initial, correct? You had to give some initial weights before you begin training. So I'm giving uniformly distributed weights to my input layer 1. Then I have second layer with 8 neurons, third layer with 4 neurons, fourth with 2 neurons, and finally I have single neuron output because my output is one dimensional. Output is y. Y is a function of x. Y is 1 plus sine x, correct? That's what we want to approximate. It's not a linear function. Remember, it's not a linear function. Sine x is not a linear function. So y as a function of x is a very interesting function, and we want to approximate it using neural network. Okay, once you are through with this model creation, the sequential library, so sequential will allow you to, this class will allow you to create a model of your choice by adding different layers. So I think the moment you go inside layer, you will get a lot of options, normalization, dense, and then dropout, and then you will get CNN. So you will have convolutional layer and so on. So a lot of layers are there in the dense. Dense is one of them. Then you can compile your model, and then while compilation, you are supposed to provide the loss function. So we say that loss is going to be mean square error, output minus prediction square, and this is going to be your loss. An optimizer is Adam. You can check on Adam. There are many different optimizers. As I said, gradient descent. These are all one or the other way of finding the optimal for the given cost function. Correct. All are gradient based. Okay, then you can summarize your model. So it tells you that in the first layer, there are 16 inputs, 16 neurons, and number of parameters are 32. Why 32? Each of the neuron has two inputs. One is the input, second is the bias. Correct. So one weight and one bias, 16 neurons, 32, total 32 parameters. What about second layer? Each of this neuron in the second layer, which is the dense layer here, would have how many inputs? 16 inputs, because it is connected to the previous layer. So there are 16 inputs coming to each neuron, and there is one for bias at each neuron. So it is 17 into 8, which is 136, and so on. So total number of parameters is 217. Then you can use model fit function, provide your training instances as input, decide on number of epochs, batch size, validation split, and then you can just run it. And then you can predict using this model that you have built on the training instances, what is the Y that you get, and then you can plot the actual versus the predicted. And you will see that the function does a good job of approximating your sine function. Okay, you can execute this along with me if you are interested, or you can just see things happening here. Okay, the second function that I have chosen is Westra's continuous everywhere and differentiable nowhere function. This is a fantastic function. It looks like this, some sort of exceptional function which has no derivative, so which doesn't have any derivative. At any point, you will not be able to find out derivative. So not differentiable, but continuous everywhere. So it's fun. Same sort of network, and then you see that it does some job, not a very good job, but it does approximate it well. Third is piecewise linear function. So this is piecewise linear function, and then you can see it latches on well. And the final one is a classification. So essentially, the red, green are all different classes. So there are red, green, blue classes, and you see that how it does the classification. So that's all. I think I'll stop here. I'm supposed to respect time, and I'll stop here. But if you have any questions, I'll be very happy to take a few questions here. Thank you. Yeah, questions, doubts?
Dear participants, you are requested to, if you have any doubts or queries, please feel free to ask, sir.
I think it's tea time. They are all waiting for a cup of tea, so let's not disturb anybody.
Yes, sir. Sir, I have a small query.
Yes.
There are two platforms in which all this machine learning AI stuff can be implemented.
There are two frameworks, PyTorch and TensorFlow.
No, I'm talking about Google Colab and Kaggle.
Oh.
So, which one would you recommend for? I mean, is there any relative difference between them, or the new users can choose any of them?
No. So I chose this Google Colab because we have integration with Google at our institute, but we don't use Google Colab for actual problem solving. For demonstration, for small problems, it is okay, because unless you go for a subscription, the data that you use will be wiped out after you use it. So, and the amount of computation which is available is not known to you. So the GPU usage or CPU you cannot monitor. So we do all the coding on our supercomputer facility. So we have our own setup, and I would recommend that for small problems you can work on Colab, or you can install TensorFlow on your machine. Without GPU also, you can at least play around with TensorFlow and PyTorch. PyTorch is slightly difficult to handle without GPU, but yeah, TensorFlow is easier and easy to implement sort of a thing. You can start with TensorFlow. I can give you links. I'll put up some links in my notes. Those who are interested can refer to these links for TensorFlow and PyTorch. There is a lot of literature available. Lot of notebooks are available. Good notebooks are available, Python notebooks, which will allow you to go through the basics of PyTorch and TensorFlow both.
And also yesterday, several people were asking, what would be a good reference book for starting with machine learning and AI, the programming aspects, etc.
So if you are looking for programming, I think the best resource would be the TensorFlow and PyTorch documentation.
Yes, sir.
If you want theory, there are good books available. But if you want to learn programming and you want to work with these frameworks, there is no other alternative but to go through the documentation. There are very nice Python notebooks available on GitHub also. Those who want to start, they can start with NVIDIA containers. I can guide you over there also. So NVIDIA has a lot of pre-built models for you. I'll just paste a link here so you can just have a look at it. I'm sure some of you might have seen this. If not, then you can have a look at it. So GitHub has NVIDIA page. NVIDIA is company which produces GPU, correct? All of us know. So
yes,
they are into high performance computing and parallel computing. So they do a lot of hardware stuff. So this GitHub repository contains a lot of interesting things, deep learning examples and so on. So maybe I can just share it here. If you allow me, I can do that for a while.
Sure, sure.
Idea is to, so you see that these Dockers are for people who are ready to deploy things, correct? Deep learning examples, if you go inside, you will see there are a lot of examples which are already created for you. So for example, computer vision, if you're working on vision problems, these models are already there. Natural language processing, the models are there. Recommender system, speech to text, text to speech. So all of this are actually being coded and made available to you as Python notebooks. So if you go inside this ResNet, let's say, so ResNet would have model overview, and then you will get all the interesting details, how to set up things, how to work on this, how to clone this repository, what to do with it. So everything is available. You just have to read and do. That's it.
Okay, thank you, sir, for your
and
nice
TensorFlow again. So TensorFlow again, you have a nice repository. The system requirements are there. You can follow these basic steps. You'll be able to install TensorFlow and start with the notebooks. I think that's the best way to begin your coding exercises.
Yes, sir. Okay. Thank you very much, sir, for sharing your expertise and time with us. I'm especially thankful to you because we are calling you on a Sunday and you have spent your valuable time with us on a holiday. Thank you very much. It was very informative. We learned a lot from you, and we hope we can have a similar sort of a tutorial in physical form when all this pandemic is over.
Definitely.
I would request Professor Mihir Mohanty also to speak a few words if possible. Mihir, sir.
Thank you, Professor Shah. I am very glad to meet you here also.
Thank you, sir. Thank you for the invitation. I hope I could be of some help.
Yes. Now you are in my bond. as Professor Patra is my teacher, like, and everything will be fine.
He is also my teacher also, Professor S.K. Patra.
Great.
Okay. Thank you very much, sir.
Thank you very
Thank
much.
you. Thank you.
Sir, you can.
I will be in touch with you.
Definitely. Thank you.
Any
Thank you.
cases, I will be in touch with you. Okay.
Okay.
Thank you. Thank you.
Have a nice day. Bye bye.
Thank you,
Bye
sir.
bye.
So, a small announcement for the participants. The feedback link for session 8 has been shared. Please fill it up. That is for attendance as well as feedback. And the next session will start at 5:15. Let's take a small break and gather here at around 5:15. Thank you.